Welcome to The Explainer. I am so thrilled to have you here today. We're going to decode the invisible digital address system that makes the entire modern internet possible. I mean, if you've ever wondered how a video you click on perfectly routes its way to your specific phone out of the literally billions of devices worldwide, well, you are in the right place. We're breaking down the internet's most fundamental infrastructure today. So get ready to have the invisible made totally visible.
Look at the staggering number, 340 undecillion. That's a 340 with 36 zeros right after it. Just kind of let the sheer scale of that wash over you for a second. What on earth could possibly require a number that astronomically large? Well, stick with me, because by the end of this explainer, you're going to know exactly why the entire future of our digital world depends on this specific gigantic number.
Okay, let's dive right into this. Here's our roadmap. First up, what is an IP address? Then we'll hit IPv4 and binary translation. Next is the great address shortage, followed by our band-aids, NAT and dynamic IPs. Then we'll get to IPv6, the ultimate solution, and finally, why is the switch delayed?
All right, section 1. What is an IP address?
So let's start right at the foundation. To communicate across the internet, whether that's via those massive underwater cables or totally wirelessly, every single device absolutely needs a numeric identifier. It's exactly like the physical mail system. Your home has a physical address, right? And it's managed by your local postman to actually physically deliver a package. If someone wants to send you a letter, they can't just guess. They need that exact location. It's the same exact thing for your computer. It has an address, the IP address. And instead of a postman, other internet-connected computers use this digital address to locate you and deliver the files or streaming media or emails you ask for.
Now, all of this relies on the Internet Protocol, or IP. This is the master set of rules governing how data is sent. It handles two huge jobs: addressing the host, which is a lot like putting a return and destination label on a package, and routing, which is figuring out the absolute best path for that data across all these different network boundaries so it doesn't just hopelessly bounce around the globe. Without these rules preventing all that misdelivery overhead, the internet would just be pure, inefficient chaos. We wouldn't be able to easily book train tickets or hunt for jobs online or use cloud storage. We'd honestly be stuck buying physical CDs. Moving on to Section 2, IPv4 and binary translation.
To really understand the current heavy lifter of the internet, which is IPv4, a foundational protocol developed way back in the late 70s, we have to look at how computers actually read data. Because while you and I see standard decimal numbers, computers definitely do not. They only understand binary, just ones and zeros. An IPv4 address is a 32-bit numeric address. To make it readable for us humans, we write it out as 4 groups of numbers separated by periods. We call these groups octets, and each one can range from a value of 0 to 255. But remember, your computer is processing this as 4 sets of 8 binary bits, creating a sequence of 32 ones and zeros.
Now, if you were going to make an animated video to explain computer translation, this is the exact kind of visual you'd want to use to really make the math click in your brain. Starting from the left, each of the 8 bits in an octet represents a specific value: 128, 64, 32, and so on, all the way down to 1. A bit can literally only be a 1 or a 0. If it's a 1, the number counts. If it's a 0, it doesn't. By just manipulating those ones and zeros, you can generate any single number from 0 to 255.
Let's actually play a quick math game to see this in action. Say we want to decode the first octet of an IP address, which is 66. How does a computer actually see 66? Well, we just look at our chart and turn on the values that add up to 66. We put a 1 in the 64 slot. We need 2 more, so we drop a 1 in the 2 slot. The rest just gets zeros. In that sequence, 010010 is exactly how a computer reads the number 66. Pretty cool, right? Which brings us to Section 3, the great address shortage.
So it's an incredibly elegant system for sure, but here is where we hit a massive wall. The internet didn't just grow, it absolutely exploded far beyond the wildest science fiction dreams of the 1970s programmers who built IPv4. A 32-bit system, mathematically speaking, can only produce about 4 billion unique addresses. Now, 4 billion might sound like a huge number, but once you do the math, it is drastically short of what we actually need today. I mean, it's simply not enough for every single smartphone, laptop, smart TV, and connected fridge on Earth to have its own unique connection point.
Those early programmers just vastly underestimated the scale of what the internet would become. And remember that fundamental rule of the Internet Protocol we talked about? Without a unique address, there's literally no way to ensure a data packet is delivered to the correct destination. Running out of these 4 billion addresses threatened to basically collapse the very foundation of how the web functions.
Section 4. Band-Aids, NAT and Dynamic IPs.
So, if we only have 4 billion addresses and there are vastly more than 4 billion devices active today, how did we make it this far? Why hasn't the internet just broken? Well, the answer lies in some incredibly clever engineering workarounds. The absolute biggest lifesaver was NAT, or Network Address Translation. Think of NAT like an apartment building. Two completely separate physical buildings can both have an apartment 804, right? In the exact same way, your computer at home and your computer at work can actually have the exact same private IP address. Their data never gets mixed up because NAT groups all those overlapping private IPs behind one single unique public street address, which is your router's public IP. It just shares that outward-facing address to save space.
This workaround ties directly into our everyday experience with dynamic and static IPs. To conserve addresses, your internet service provider gives everyday users dynamic IPs. They basically just assign you an address from a shared pool for the time you're connected. Next time you log on, you might get a totally different one. It saves a ton of space. Static IPs, on the other hand, are permanent. They never change. They're essential for crucial infrastructure like DNS servers. Those are the computers that actually help you open websites. Because static IPs don't change, they provide persistent info, tracing physical locations right down to the continent, country, and even the ISP of the device.
All right, Section 5, IPv6, the ultimate solution.
But listen, NAT and dynamic IPs, they're really just band-aids. They add performance overhead and make peer-to-peer connections way overly complex. The internet needed a permanent fix. Enter the ultimate real estate solution, IPv6. IPv6 is this massive, ground-up numerical upgrade. Instead of 32 bits, it uses a 128-bit address length. To keep it even somewhat readable for us, it uses hexadecimal formatting, separating 8 sets of 16 bits with colons. This upgrade is exactly what generates that staggering 340 undecillion possible addresses we saw right at the beginning. That is enough for every single person on Earth to have billions of addresses for every device they will ever own. Plus, it brings huge performance boosts. Devices can auto-configure themselves, and the header data is stripped of extraneous baggage to reduce transmission overhead.
Let's look at the math real quick, because converting 128 binary bits into something readable requires a neat trick. IPv6 compresses 4 binary bits into a single hexadecimal character. If the bits represent 8, 4, and 1, they add up to 13. But hexadecimal uses single characters. You can't just write 13, so we use the alphabet to represent sums of 10 or higher. 10 is A, 11 is B, 12 is C, and 13 becomes D. It's honestly a brilliant way to compress massive streams of binary into shorter alphanumeric strings.
Finally, Section 6. Why is the switch delight?
So with all these incredible benefits, endless addresses, better peer-to-peer performance, no more clunky NAT, you'd think everyone would be absolutely thrilled to migrate immediately. So why in the world didn't we fully flip the switch a decade ago? Believe it or not, modern PC operating systems and mobile phones have actually been IPv6 capable for a long time. The issue isn't our consumer devices. The core problem is compatibility. An IPv4 system simply cannot natively access an IPv6-only website. There is zero built-in backwards compatibility between these two protocols.
So, the crucial point here is that the real roadblocks are the internet service providers. Upgrading their massive infrastructure to dual-stack gear that handles both IPv4 and IPv6 simultaneously is incredibly expensive. On top of that, they can't easily market the benefits of IPv6 to an average customer who just wants to browse the web. But perhaps most critically, and this is huge, adopting IPv6 removes the need for carrier-grade NAT. While NAT causes overhead, it also gives ISPs a great deal of visibility and control over the traffic going in and out of their networks.
Which leaves us with this final, truly vital question to ponder. Will the relentless consumer demand for a faster, simpler, more robust internet eventually force ISPs to swallow those massive costs and give up that traffic control? This touches right at the heart of the net neutrality debate. I highly encourage you to dig into this tension between infrastructure costs, ISP control, and digital freedom. Because how this plays out, it's going to dictate the foundational architecture of the internet for generations to come. Thank you so much for joining me for this explainer. I really hope it brought some clarity to the digital world right at your fingertips. Keep learning, and I will catch you next time.